Yo, what up, everybody? Coming at you today with a video about net force and how the net force affects motion. So we're going to talk about what net force is, and we're going to talk about how you can predict the effect on motion once you know the net force. Okay, like what happens if the net force is in the same direction as a motion? What happens if the net force is in the opposite direction? What happens if the net force is balanced? So first, what is net force? Look at this free body diagram here. You'll notice that there are 4 different forces on this object. And so there are forces in all direction, but the top force and the bottom force are the same size and in different directions. So they cancel each other out. And the forces on the left and right are also the same size and in different directions. And so they cancel each other out as well. Once these cancel out, you're left with the net force, which is what's left after everything is canceled out, and that's 0. Next example, you can see there's also 4 forces on this object. The top and the bottom will cancel each other out. The one on the left is smaller than the one on the right. So it cancels out some of the force on the right, but not all of it. And what you have left over once opposite forces cancel each other out is this little bit of the rightward force. All right, and so our net force would just be that force there. That's what's left after things get canceled out. And so in this case, the net force is not 0. If we had numbers for like the newtons of force, we would just subtract to find the net force. All right, so let's look at an example of a balanced force, and we're going to kind of see how this affects the motion. So this car is calibrated so that its applied force is equal to its friction force, and on a flat surface, its normal force and gravity are also equal. So we have a balanced force right here, and let's see what happens to the car. So the car moved, and if you were to measure its position every so often, you would see that it moves the same amount each time. All right, so you have these dots showing where it was, and if we were to graph this motion on a position time graph, you would see that as time went on, the position goes up by the same amount. Right, so this is an example of constant motion, which is what you see when you have balanced forces. If we do a velocity versus time graph, we just get a straight line because the velocity is a measure of the slope of the position versus time graph, and that slope doesn't change. So that's balanced forces. Now let's look at the example where there's a net force. There's more force on the right than on the left, and the motion is also in the rightward direction. So this little car here has a tension force that's being pulled by a string, has a tiny bit of friction, but the tension force is definitely greater than the friction, causing an unbalanced force. And let's see what this car does. So if you were to measure where this car was at any given time, you would see that these little dots that you put down would get further and further apart, because every moment that goes by, the car is going a longer and longer distance, and that's because it's going faster. So if you were to graph this on a position versus time graph, you would see that when these dots are close together, the position only rises a little bit, but once the dots get farther apart, the position rises a lot. And so the position time graph would look like this. It would curl upwards, and that's the sign of something that is speeding up. You're going to have a curl upwards in the position time graph. And so the velocity graph, velocity follows the slope of the position graph. So you can see that where the slope is low, the velocity is low, and where the slope is high, the velocity is high. Now let's look at an example of something that is where the net force is opposite the direction of motion. So this is a box, and somebody pushes a box, and it slides along the table. Now that it's been pushed, there's no other force on it, and so it's just going to slide until it comes to a stop. But the friction is going to be on it the entire time. And so while it's sliding, it has a force of friction to the left and no force to the right. And so let's see what this object does. So as expected, the box comes to a stop. But if you're to measure its position at some given times during its motion, you would see that the position markers are going to be far apart in the beginning and they get closer and closer. That's a sign of the box slowing down. So for our position time graph, in the beginning, the line is steeper because the position changes more every second. But as time goes on, the position changes less and less, so you get a less steep line. So translating this to a velocity versus time graph, you have the largest velocity in the beginning, the smallest velocity at the end, and it comes down to the zero line here when the box comes to a stop. All right, and so that's a result of the motion being in one direction, but the net force pushing it in the other direction. So to sum up what we've learned, right, if you have balance forces, there's two options. The object could be not moving at all, and in which case it's just going to continue not moving, or it could be moving at a constant velocity, and it's going to continue moving at that constant velocity until it encounters a net force of some type. The net force could be in the direction of the motion, in which case the object is going to speed up, or the net force could be in the opposite direction of the motion, in which case the object is going to slow down. All right, so these are the three possibilities, and this is how we can predict what's going to happen to the motion over here if we know what is true of the net force over here. All right, so hopefully this video helped you understand net force and motion, and I'll see you all in another video.